Hello everyone, we do hope you are doing well from wherever you are. Thank you for stopping by to our channel to watch this video. In the today's project, we are going to build logic gates using transistors. Ideally, logic gates are all available as an integrated circuit. These chips are inexpensive and often has 3 or more gates in them. However, there are times when your circuit requires only one logic gate. This makes it sound better to simply build one with transistors instead of using an entire chip. Or, let's say the logic gate chip you want to use at that moment is not available. We will construct all basic logic gates, OR, AND, NOR, NAND, exclusive OR, and inverter. Let's dive right in. OR gate. The first on our list is the OR gate. This is constructed using 2 transistors as shown in the circuit diagram. Let's build it on a breadboard and generate its truth table. Well, here is a completed circuit. Let's test it by driving its inputs A and B high and low to check its functionality. Currently, both input A and B are at logic 0. And as you can see, the LED at the output is off, indicating we have a 0 at the output. If we press input A button, the LED comes on, indicating a logic 1. Doing the same for input B also turns on the LED. Let's now press both A and B button and see the result. As expected, the output remains high, and the truth table of an OR gate is generated. NOR gate. This is an inversion of OR gate. We achieve this functionality by passing the output of an OR gate through an inverter, which is implemented using the 3 transistors shown in the circuit diagram. As with OR gate, let's build it and generate a truth table. The completed circuit on a breadboard should look something similar to this. As you can see, the inputs at A and B are all 0 and the output is already high. Let's fill this state up in the truth table. Pressing it turns off the LED, and the same results when B is pressed. Again, let's add the 2 states to the truth table. Lastly, let's press both A and B to see the result. The LED turns off, an indication of logic 0. A completed truth table shows a complete inversion of OR gate, which is what you can achieve with a NOR gate. AND gate. AND gate also uses 2 transistors as shown. But instead of connecting them in parallel, they are in series. Ideally, the LED should only turn on when both transistors are on. Let's construct the circuit on the breadboard to see what happens. Currently, both input A and B are at a logic 0 and the LED is noticeably off. Let's add that to our table. Pressing either A or B buttons does not turn on LED. The output remains at logic 0, quickly filling up the next 2 rows in the truth table. However, the LED turns on when both input A and B are high or when the 2 buttons are pressed at the same time. A complete AND truth table is as shown. We are doing quite well. Let's move on to the next logic gate. NAND gate. As with OR gate, an inversion of AND gate is called NAND gate or simply not AND. Can you predict what the NAND's truth table will look like? Let us give you a minute to think and leave us your sincere answers in the comment section whether you got it right or wrong. Also, consider subscribing to our channel if you haven't done so. Thank you. The circuit on the breadboard is also implemented using 3 transistors. The first 2 forms the AND gate and the third one is for inverting the output. Input A and B are currently at logic 0, but the output is already at logic 1 since our LED is turned on. Add that to the truth table and let's proceed. Pressing button B doesn't change the output state. It remains at logic 1. The same for input A. LED remains on when either inputs A or B is high. Now, let's press both A and B buttons to see what happens. There you go, the LED finally goes off. When both inputs are high, the output goes low, and that verifies the truth table of a NAND gate. Exclusive OR gate. This is a bit complex to construct on a breadboard since it combines the functions of both OR and NAND gate. The two logic gates are united with a fifth transistor. We will come back to how it works later, but for now, let's build the circuit and generate the truth table. Here is the circuit on the breadboard. Both inputs A and B are at logic 0, and noticeably, the output is also at logic 0. That is the first state. Pressing input B to drive it high turns on the LED, a logic 1 at the output. Doing the same with input A gives the same result. Let's fill them up in our truth table. The last is where this exclusive OR gate differs with OR. Let's see what happens here. Pressing both A and B buttons turns off the LED, a logic 0 at the output, and out truth table is now complete. But how does the circuit achieve it? As you can see, the circuit first operates as an OR gate. The output is off when both A and B are at a logic 0. Pressing either A or B turns on the LED, perfectly as an OR gate would operate. But when both A and B are at logic 0, the two transistors of the AND gate are turned on. This provides a new path of less resistance for the current to flow to the ground. That action turns off this transistor, consequentially disabling the OR gate. There is no path for current to flow to the ground. The LED is, therefore, turns off. Buffer. This is not so exciting logic gate but still useful in some applications. Simply put, whatever is at input A appears on the output. When A is at logic 0, output is also at logic 0 and vice versa. Inverter. This is also not so exciting but very important in most applications. We have just seen it in action in NOR and NAND gates. Different inverter circuits exist, but the simplest one is as shown. As the name implies, it negates what is applied at the input A. If it is at logic 0, the output becomes a logic 1. And if you drive the input high by pressing the button, you get a logic 0 at the output. The completed truth table is as shown. Thank you for watching this video to the end. We have more exciting DIY electronic project videos on the channel that can draw your attention. Check them out if you have a minute and don't forget to subscribe to support us. See you in our next videos and have a blissful day ahead.